Page 523, lesson 8.7 is on factoring special cases. We've got a couple different cases we're going to be looking at in this section. So one of these is factoring perfect square trinomials. So just if you look at this bottom example here, so they had 4n squared minus 12n plus 9, and they factored it, and it factored as 2n minus 3 times 2n minus 3. So there's nothing different there. The only difference is that if you'll notice, those binomials are identical to each other. So a shorter way of writing our answer then, we could say it's the quantity 2n minus 3 quantity squared. Okay, just because those binomials are identical. So to me, the book makes a big deal. They call it a special case. It's pretty much the same. It's just that we can rewrite it different at the end. Okay? And the book talks about at the bottom of the page here how we can recognize that we have a perfect square trinomial. So if you're interested in looking at that part, you can look at that as well. So if you look at problem 1, they want us to factor this. So to factor this, the book goes through their whole process again. If you want to do it that way, you can. If you want to just do it like we've been, then that's fine too. We've got a plus 36 and we've got a negative middle term. So we know we have to have both negatives. And we need 12 negative x, negative 12x for our middle term. So if you have 6 and 6 gives you 12. So this would be it. And then again, since these are both identical, we can rewrite it as x minus 6 quantity squared. So let's go ahead and look at the got it one. We look at part A. They want us to factor this. So we know we need x times x to get x squared. Both signs are going to be positive. To get the 9, we either need 1 and 9 or 3 and 3. If you do 3 and 3, that'll give you 3x plus 3x is 6x. And then coincidentally here, these binomials are both the same. So we can rewrite that as x plus 3 quantity squared. So if we look at part B, same idea. We know to start with, we need x times x to get x squared. We have a plus 49 at the end, means both signs are going to be either positive or both signs are going to be negative. Since we have a negative 14x in the middle, these are both going to be negative. And factors of 49, if we try 7 and 7, that's minus 7x minus 7x gives us the minus 14x, negative 14x. And then binomials are both the same again, so we could write that as x minus 7 quantity squared. Problem 2, digital images are composed of thousands of tiny pixels rendered as squares as shown below. Suppose the area of a pixel is 4x squared plus 20x plus 25. What is the side length of one pixel? Okay, so if that's the area and it says it's a square, well, we know on a square the length and the width are both the same. So what that means, to find the area, we do length times width. So we need to find two binomials that both factors, both binomials are the same. And so the book went through their process. We could otherwise do like we've been doing these. And we'll get the same thing. So 2x plus 5 quantity squared is our area, or we could just actually go from this here and say that the length of one side is 2x plus 5. Both dimensions would be 2x plus 5 there. So similar idea on the got it 2. You're building a square patio. and the area of the patio is 16m squared minus 72m plus 81. What is the length of one side of the patio? All right, so once again, they are telling us it is a square, so we know our binomials have to be identical, which really majorly limits our options and makes it a lot easier for us to work this problem out. So with 16m squared, if these both have to be the same, it would have to be 4m times 4m. We have a plus 81. Our middle term is negative, so both of these will have to be negative. And then for the 81, if these are both going to be identical, they'd both have to be 9s. Technically, the question is just what's one of the side lengths. So at that point, we could say one of the side lengths is 4m minus 9. We don't really have to rewrite it as 4m minus 9 quantity squared because they're just asking a side length. They're not asking us to like factor it completely or anything. Back in section 8.4, we had something like this, a plus b times a minus b. And when we FOILed that out, the middle terms canceled out. We're left with a squared minus b squared. So the other direction we can go and we can factor something out. So we're going to be doing a problem kind of like this. 25x squared minus 36. And we're going to factor that. The deal is if you only have two terms, in order for it to factor into two binomials, the factors, the binomials have to be identical except for the signs. One has to be positive and one has to be negative. Okay? It'll always end up like this. If you only have two terms, it'll always end up like this, where these are the same except the signs will be different. Okay, so again, not many options that we have, and that makes it a lot easier for us to factor difference of squares, as these are called. So if you look at problem 3, they want us to factor z squared minus 9. So z squared minus 9 is going to factor as z plus 3 times z minus 3. So if you look at the got it 3. So for part A, if we're going to factor this, to get v squared, we need v times v. And this is a difference of squares, so one of our signs should be positive and one should be negative. And both of our numbers would have to be 10. 10 times 10 to get 100. And again, what that does is that makes our middle terms cancel. We've got minus 10v plus 10v cancels, and that gives us to where we only have the two terms. So that would be our factored form for that problem. If we look at part B, same idea. There's only two terms, so it should be a difference of squares. And you can look also, the book talks about, both of these should be perfect squares if it's a difference of squares, is another way of helping you to see that. So we need s times s to get s squared. One will have to be positive, one will have to be negative. And the numbers have to be the same. They'd both have to be 4s. That would give us the minus 4s plus 4s cancels out, and that gives us s squared minus 16 then, if we would distribute that. Problem 4 is really very similar. The only thing they've done is they've added a number in front of our squared term. So 16x squared minus 81 is going to factor. It'll be 4x plus 9 times 4x minus 9. So if you look at the got it 4, part A, same thing. We've got 25d squared minus 64. So to get the 25d squared, we would have to have 5d times 5d. And again, there's only two terms. This will have to be a difference of squares, so the signs will have to be opposites of each other. And then to get 64, we need 8 times 8. Once again, the middle terms will cancel. You'll have negative 40d and a positive 40d cancels out. So that should be our answer for that one. So we've kind of been not really talking about it so far in this section, but if you'll remember, we've talked about previously the first thing we should really do on problem is look for greatest common factor. So that is being reintroduced here on problem 5. If you look at that, you might say, oh, it's two terms, difference of squares. The problem is 24 and 6 are not perfect squares. Like a number times itself to get 24, no. 5 times 5 is 25. 4 times 4 is 16. I can't have a number times itself to get 24. Same idea for 6. What I can do, though, is factor out a greatest common factor. So that's what the book did here. GCF of 6 gets us to this point, and then now we can factor that because 4 and 1 are both perfect squares. So always just make sure you try and look for that GCF first before you start going on these problems. So if you look at the Got It 5 Part A, they're wanting us to factor that. So this problem, actually there is a 12 as a greatest common factor. That would leave us t squared minus 4. And now t squared looks good. 4 also is a perfect square. So t times t to get t squared. 1 positive, 1 negative. And then if we put 2's in both of these places, that'll cancel out those middle terms, which is what we want. So this would be our factored form for part A. So same idea if we look at part B. Again, 12 is not a perfect square. And actually this one has 3 terms in it. So they've gone back away from our difference of squares here, right? Difference of squares would only have 2 terms in it. So this one, GCF is 3. That'll leave us with 4x squared plus 4x plus 1. Like I said, this has 3 terms in it still. It's not a difference of squares. It might be something else we've talked about in this section possibly. So to get the 4x squared, let's try 2x times 2x. All the signs are positive, so these will both be positives. To get the 1, we'll need 1's in both of these spots. You can check this, the middle term. That's 2x plus 2x is 4x. And then since those binomials are identical, we can rewrite that as 3 times the quantity, 2x plus 1, quantity squared. If you look at number 52, they want us to factor this expression. And probably notice right off the bat the difference here is that we have 2 variables instead of 1 variable. The process is the same. And just remember always our first thing is to try to look for a greatest common factor. Well, the p to the 6th power, there's no number in front of it, so I can't factor a number out possibly. The last term doesn't have p in it, it just has q, so there actually is no GCF. We're just going to factor this just like it is. So to get p to the 6th, we need p cubed times p cubed. There's other possibilities, but notice our middle term has a p cubed in it, so that's a good indication that that's probably what we want to do. All our signs are positive, so we'll put positives in both spots. And then for the 400, we could do 20 times 20. The difference is here we've also got this q squared, so we need to put q's behind both of those. And then check your middle terms. This is 20 p cubed q and 20 q p cubed. You can switch it around, and it's the same. Those are like terms. 20 plus 20 is 40, so that works. And then notice these are identical to each other. So our final answer, we could have p cubed plus 20q quantity squared. So this gives you an idea of how to factor special cases.